Alright, this is problem 2 for the 5 problems extra credit for exam 4, and it's a problem from the book, and it reads as follows. Predict whether the following reaction would proceed spontaneously as rated at 298 Kelvin. And then they give us the reaction of cobalt solid plus iron 2 aqueous yields cobalt 2 ion aqueous plus the iron solid. And they tell us that the concentration of the cobalt 2 is 0.15, and then the concentration of the iron 2 ion is 0.68. And so what we have to do to solve this equation is first and foremost understand what they're giving to us. They're giving to us concentrations for our products and for our reactants, meaning that they're not at standard condition, meaning that they're not each like 1 mole or 1 molality or whatever. Concentration is not 1. And so since it's not at standard conditions, we're gonna have to use the Nernst equation, which is the non-standard EMF is equal to the standard EMF minus the constant of 0.0257. Well, what happened there? 257 volts over the moles times the ln of Q. So we've written down the equation we're going to use, and we also know that our Q is the concentration of our products over the concentration of our reactants, and that we don't include the Fe solid, the iron solid, and the cobalt solid because they're solids, and they shouldn't be included since their concentrations aren't really going to affect that much the overall reaction. And so now what we have to do is we have to write down the half reactions for both our iron and our cobalt, and they're going to be as follows. So our half reactions for our cobalt and our iron look as follows. And if you're wondering where I got the 2 electrons there on that side and then on this side, I just basically added it to the side that has, for example, the ion here in order to balance out the equation on each side, so that the overall charge will be the same on both sides. And to do that, well, since here our charge for our iron is 0 and over here our charge for our cobalt solid also is 0, and we want to balance it out in order to cancel out this 2 plus. And on both sides, for each, we have to add 2 electrons to basically balance out both equations. And then, as we can see here, our cobalt is being oxidized because it's losing electrons. And then our iron here, it's being reduced because it is gaining electrons. And so since we know that our equation that's getting oxidized, or our element, whatever that it's getting oxidized, is going to be the anode, and the one that's getting reduced is going to be the cathode, because that's always as so with the galvanic cell. And then in the book, it tells us that for our half reactions for cobalt, from when cobalt is getting reduced in the reaction, the standard reduction potential at 25 degrees Celsius is negative 0.28, but here we've reversed the reaction and it's getting oxidized, so it's going to be positive 0.28. And then for our iron, when it's getting reduced, it is negative 0.44 for its standard reduction potential. And that's given to us in a chart in the book. And now, since we have the potential for both of our half reactions, we can use that to find our standard EMF here. And then our standard EMF of the cell is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode. And we have both up here, and so all we have to do is plug them in. And then after we've plugged them in, we find that our standard EMF is equal to negative 0.016 volts. And now we're going to use that number and plug it into our overall Nernst equation. Okay, and we had some technical difficulties while I was recording, so bear with me if things don't look the same. However, here all I did after I got the standard EMF over here is I just rewrote my equation, my Nernst equation, and I just plugged in the information that they had given me, the concentration of cobalt, the cobalt ion, the concentration of the iron ion, the standard EMF that we had calculated, and the number of moles of electrons that were being transferred, which is, as we can see here, it's 2 overall. And so I just plugged that in, and remember that our Q is equal to the concentration of our products over the concentration of our reactants. And then all we have to do now is plug it into our calculator to solve for E, or our non-standard EMF. And so after we plugged everything into our calculator, we found that our non-standard EMF is equal to negative 0.14 volts. And since our non-standard EMF is negative, it's non-spontaneous. So therefore, our reaction is non-spontaneous in the way that they gave it to us. Thank you.